morning, everyone. Dr. Ashish is ready with his presentation, so we should not make him wait for too long. Sir, please continue with your talk.
Okay. Good morning, everyone. So we will be continuing our discussion regarding the BGW MPC protocol that we started discussing yesterday. So we will first consider a simple case where the parties would like to compute securely a linear function. Okay. So the theorem statement here is the following. Say we have a set of n parties and they are connected by secure channels. And the function which they want to compute has this form. So here x1, x2, xi, xn are the respective inputs of the parties. And c1, c2, cn, they are also elements from the field, but they are constants and publicly known. However, the respective inputs of the parties, they are available only with the parties, with the respective parties. So x1 is available only with p1, x2 is available only with p2, xn is available only with pn. And it is easy to see that this is the generic form of any linear function. So the theorem states that there exists a secure protocol, okay, which allows the parties to compute the value y securely, even if up to t parties are compromised by an adversary, where t is less than n. Okay, that's the statement. So now let us see the proof, and the proof will be in the form of a protocol. So here is the protocol for securely computing any linear function. Okay. So the first step will be that each party will be secret sharing its own input among all the parties. So x1 is secret shared. And who will be secret sharing x1? Party p1. So he will compute a vector of shares for x1. How it can do so? It can pick a t-degree polynomial whose constant term will be x1, evaluate that polynomial at those publicly known values alpha 1, alpha 2, alpha n. That will give him this vector x11, x12, x13, x1n. In this particular demonstration, I am assuming n is equal to 4. But in general, the protocol works for any n and any t, where t is less than n. Okay. So he will be secret sharing his input, and he will be keeping his share with himself, and remaining shares he will distribute among the parties. So the second share is given over the secure channel to the second participant. The third share is given to the third participant. The fourth share is given to the fourth participant. Okay. So at the end of this step, everyone will now have a share for the value x1. Okay, so in their respective circuits, they will think as if they have got now a share for the value x1. And the same thing is done by other parties as well. Okay, so P2 will now act as a dealer. Independently, it will be picking a t-degree polynomial whose constant term will be x2. Evaluate that polynomial at alpha 1, alpha 2, alpha 3, alpha 4. Keep one share with itself, namely the share x22. And give the remaining shares to the respective parties. So now at the end of this step, everyone will have a share for the input x2. Similarly, P3 will do the same thing, and P4 also will do the same thing. Okay, so at the end of this step, all the inputs have been secret shared. Now they go to the gates, which have to be evaluated. And since we are assuming a linear function here, all the gates here are linear gates. And now we can trigger the linearity property. The linearity property of Samir's secret sharing. So what the parties are now going to do is the following. They know the values of C1, C2, C3, and C4. Their goal was to compute the function C1 times X1 plus C2 times X2 plus C3 times X3 plus C4 times X4. But the values of X1, X2, X3, X4 are not available in clear, but rather their shares are available. So what each party is going to do is it will apply the same linear function on the shares of X1, X2, X3, X4, rather on the exact values of X1, X2, X3, X4. So P1 will compute this value. It can do so because it has the shares of X1, X2, X3, X4, his shares. And anyhow, C1, C2, C3, C4 are publicly known. P2 will independently do this computation. P3 will independently do this computation, and P4 will do this computation. This does not require any interaction among the parties. The interaction was required only for secret sharing the inputs X1, X2, X3, X4. Now, once the parties have computed their respective shares of Y, there are no more gates left in the circuit. Okay, so what they can do is each party broadcasts. So each PI broadcasts share YI to everyone. That means P1 will send Y1 to everyone. P2 will send Y2 to everyone. P3 will send Y3 to everyone. And P4 will send Y4 to everyone. And after that, the full vector of Y shares will be available with all the four parties. And now they can apply the interpolation and reconstruct back the t-degree polynomial whose constant term will be y, and hence they can obtain the value y. Why they will be able to reconstruct a polynomial through which y is secret share? Because we are working under the assumption t is less than n. And this vector of shares of y, they are the points on a t-degree polynomial. So since the value of t is less than n, we have more number of points than the number of than the degree of the polynomial. Hence, by applying the interpolation, so everyone will apply the interpolation on alpha 1 y1, alpha 2 y2, alpha 3 y3, alpha 4 y4. They will apply the interpolation and get the y polynomial, and the constant term of that y polynomial will be the value y. And that's the end of the protocol. So now let us analyze the complexity of this protocol, how many times the parties need to interact with each other, which is basically the round complexity, how many rounds are involved in the protocol, and what's the communication complexity of the protocol. That means how many bits are communicated in the protocol. So where exactly is the interaction needed in the protocol? Interaction is needed for sharing the respective inputs of the party. Now you might be wondering that when P1 is sharing the input, P2 will be able to share its input or not. That means should P2 wait for P1 to finish its part of the sharing and then proceed? Or can P2 in parallel secret share its input when P1 is secret share? What do you think? Can the parties share their respective inputs simultaneously, or it has to be done sequentially? That means first P1 should secret share, then P2 should secret share, then P3 should secret share, then Pn should secret share. Right? So parallel can be done, yes, because there is no dependency, because P1, he is picking a t-degree polynomial to share its input x1, and he just has to send the shares over his channels. At the same time, no one prevents Pi to compute the shares of xi and send it over her channel. Okay, So it will be a one round affair. Don't think it will be a n round affair. No one prevents you from doing this step in parallel. So it's a one round protocol, sorry, one round step. And how much communication will be required? So asymptotically, P1 has to distribute order n share. Of course, he don't have to give his share to himself. It can keep it with itself. So it should be n minus 1, but in asymptotic notation, or n minus 1 is same as order of n. So he has to communicate order n field elements. Why field elements? Because each share is an element of F. Okay. Remember, shares are field elements. Secret are also field elements. So P1 has to distribute order n field elements, and each field element can be represented by these many bits. So that's why P1 has to communicate order of n times log of F number of bits. P2 also has to communicate the same number of bits, and like that, since we have total n parties, this is the total communication. Where else is interaction required? For evaluating this gates, no interaction is needed because we are using the linearity property of secret sharing. And then finally, interaction is needed for reconstructing this function output y, because everyone has to give their respective shares of y to everyone else. Then only they can recover the full polynomial. Okay. So what was happening in the protocol? Every party would have communicated its individual share for the y value. Okay. P1 would have computed y1, P2 would have computed y2, Pi would have computed yi, and Pn would have computed yn. And then they would have sent, P1 would have sent y1 to everyone. P2 would, that's a broadcast step. P2 would have broadcasted y2 to everyone, so on. So this will be again a one round affair, and it will require this much amount of communication. Now, question for you. Since this is some lecture series, let me ask you a question. Can you do the reconstruction of y with 2 rounds, but order n times log of f bits of communication? That means I am now allowing you more rounds. Right now, the reconstruction is happening by asking everyone to broadcast y, broadcast their respective shares of y, which will require 1 round, fine, but it requires n squared times log of f communication. I am giving you a flexibility. I am saying that, okay, for me, communication is very critical because my channels are not very bandwidth efficient. Okay, I have bandwidth constraints. I can allow you only a total amount of order of n times log of f bits of communication. But I am fine if you let the parties talk with each other for multiple times, more than 1 round. Can you do this? Is it possible to do the reconstruction in 2 rounds, but with order of n times log of f bits of communication? Very good. So Shreyas, was that a fluke, or how you got this answer? Or have you seen the slides already, or what? Okay, very good. Actually, that's a solution. Okay, very good. So here what's happening is everyone is sending their shares of y to everyone, so that simultaneously everyone can reconstruct y at the end of that round. But now a modified reconstruction could be the following. In the first round, let everyone send their shares of Y to only one party. And we can decide who can be that party. Suppose we designate the first party here. That, okay, everyone will be sending their respective shares of Y to only you. Fine, that will take away one round. Then this party will be able to reconstruct Y. This will require how much communication? Everyone is now sending only one field element to only one party. So order n times log of f communication. Now in the second round, this party can broadcast Y to everyone. This will again require order of n times log of f bits of communication. So you can see, we can do a trade-off here. If bandwidth is a constraint for you at the time of reconstruction, but the number of times you are interacting is not a concern, then you can choose which method of reconstructing Y you go about. Okay. So there was a question by someone. Dharani, yes, what's the question? Okay, good. Fine. So let us proceed. Okay, so let me quickly give you an example. Okay, how exactly the BGW protocol would have been executed. So I'm taking a concrete function here, a very simple function. 4 friends are there. They want to find out the average of their salary. To find the average, basically you have to compute a sum. Once you compute the sum of the 4 values, you can divide it by 4 and get the average, right? So x1, x2, x3, x4 are the respective salaries. Oh, this is bad example. Salary can't be 2, 1, 0, and 1. Well, you can imagine that suppose x1, x2, x3, x4 denote something. And together they want to compute a summation of the 4 values. And they want to do it securely, even if up to 2 parties may get corrupt. Which 2 parties, we don't know. So since n is equal to 4 here, we have to work over a field of size at least 5. So I'm picking the field Z5. What is Z5? Z5 will have the elements 0, 1, 2, 3, and 4. And this +5 operation means addition modulo 5. And addition modulo 5 means you first add the 2 values, but the result will be the remainder which you obtain after dividing the sum by 5. And this multiplication is multiplication modulo 5. Okay. So now what was the first step? The first party has to secret share its input. So it has to pick a polynomial of degree 2. So it has picked a polynomial of degree 2. Don't think that the coefficient is 0. That means it's not a polynomial of degree 2. My definition of polynomial of degree 2 is it has t plus 1 coefficients. Some of those coefficients could be 0 as well. Of course, the constant term will be the value which P1 wants to secret share. So suppose it has picked this polynomial. And it will evaluate this polynomial at these values, 1, 2, 3, and 4. Okay. Remember all the addition here. This plus operation is basically plus mod 5, and all the multiplication operations are also multiplication mod 5. So if you evaluate this polynomial at 1, you will get the value 2. If you evaluate this polynomial at 1, you will get 2. If you evaluate this polynomial at 1, you will get 2. If you evaluate this polynomial at 4, you get 2. So these will be the shares. It distributes the shares. Now P2's turn. P2's turn to share 1. Suppose it picks this polynomial. Okay. Remember, the polynomials are randomly chosen except the constant term. And now If this polynomial is evaluated at 1, 2, 3, 4, where all the addition and multiplication operations are done modulo 5, the shares will be 2, 0, 0, 2. The shares will be distributed. Similarly, P3 can pick this polynomial. So you can imagine that it is 0 times z square. And compute a vector of shares, distribute, and P4, suppose, picks this polynomial, and that will give this vector of shares. Right? Now, what is the computation? The C1, C2, C3, C4 are all ones there. So now parties just have to add their respective shares of X1, X2, X3, X4. So P1 will add all this share and do modulo 5. That will give him the first share of Y, which it broadcasts to everyone. P2 computes its share of Y, which it broadcasts to everyone. P3 computes its share of Y, broadcasts to everyone. And P4 computes its share of Y and broadcasts to everyone. At the end of this step, everyone will have the full vector of shares for Y values. And that, when interpolated, will lead to this polynomial of degree 2. And what is the constant term of this polynomial? The constant term of this polynomial is 4. So everyone will take Y is equal to 4 as the output. And indeed, if X1 is 2, X2 is 1, X3 is 1, and X4 is 0, Y is going to be 4. Is the execution clear? How we are taking Shamir X2? Oh, you have to pick a polynomial of degree 2 because we are taking t equal to 2 here, whose constant term will be the value of X2. Evaluate that polynomial at alpha 1, alpha 2, alpha 3, alpha 4. That's a summary sharing algorithm, which we discussed yesterday. Is it clear? Right. Is the execution clear? Now, suppose next time again they would like to compute X1 plus X2 plus X3 and X4, and suppose they have the same X1, they have the same X1, X2, X3, X4. Then don't think they will pick the same A polynomial, B polynomial, C polynomial, D polynomial. Next time again, they might be picking random A, B, and C, D polynomial, and so on. Okay, right. Now, let us see whether this protocol maintains the privacy or not. Again, I'm demonstrating it with example, but you can intuitively think why it is secure. So remember, we took the case where n is equal to 4 and t is equal to 2. Any two parties may get compromised. We don't know which two parties. Suppose it's P1 and P4 who are compromised. They are compromised mean adversary has seen all the messages that P1 and P4 has communicated in the protocol, that they have received in the protocol, and the inputs of P1, P4. That whole thing, that whole bunch of information which adversary sees in the protocol, in cryptographic protocol theory, we call it as a view. And the view of an ADV denotes adversary here. So the view of the adversary in this execution has been shown in bold. So since P1 is corrupt, adversary will know that its input is 2. And it will know that, okay, P1 has computed this vector of shares and communicated. But it will not know what was X2. But corresponding to X2, P2 has received, P1 has received the share, which will now be learned by the adversary. And P4 has received a share, which will be learned by that person. Same holds for P3, same holds for P4. But X4 is now fully known to the adversary and all the shares of X4, because P4 is assumed to be under the control of the adversary. In addition, all the shares of Y were made public. So that's why that is also there in the view of the adversary. And then adversary has learned the output Y. Is this thing clear? The notion of view and why certain values are bold here and certain values are non-bold. Through bold thing, I'm trying to denote what adversary has actually seen in the protocol. Okay. The remaining things are unknown for the adversary. Yes or no? Assuming P1 and P4 are corrupt. Right? Now, what adversary would try to do? He may go home. He has all the supercomputers, infinite resources, everything. He will try to analyze this view that, okay, I have seen second party giving me the share 2, and the share 2. Third party giving me the share 3 and 4. And I have seen 2, 1, 1, 2 as the shares of Y, which would have resulted in the output 4. And I know that P1's input is 2 and P4's input is 0. And then he would try to learn what exactly are X2 and X3. That's the goal of the adversary. If our protocol is secure, then he should not be able to learn X2, X3, right? That's what we want to show here. Now, is it the case that adversary does not learn anything about X2 and X3 through the bold values? Or is there something which is always leaked to the adversary here? Well, the thing is, since adversary knows that the first input was 2 and the fourth input was 0 and the final output was 4, he definitely knows that either X2 could be 1, X3 could be 1, or X2 could be 2, X3 could be 0, or X2 could be 0, X3 could be 2, or so on. Various cases which are possible, right? This much information he will always learn. But that's not a breach of privacy. What was the goal of MPC? The goal of MPC was to ensure that the corrupt parties learn only as much as they can learn from their own inputs and the function output. The adversary's own input is 2 and 0, fine. And the final output is 4. From that, he can always conclude that these are the various possibilities for X2 and X3. What we want to ensure is that among all these possibilities, he should not be able to narrow down what exactly was the case. That means whatever he could have concluded about X2 and X3 based on just the inputs and output, that much only he should be able to conclude even after analyzing the messages, the shares, which have been computed and communicated in the protocol. Is this point clear? Take the case of bidding example, right? Yesterday's. At the end of the bidding protocol, if all the losers will know, fine, that their bids are individually less than the winning bid in magnitude. But the privacy that we want to guarantee there is that apart from this, no one else should learn the exact value of the losing bids. Same thing is happening here also. My function was X1 plus X2 plus X3 plus X4. Now, if two of the parties are corrupt, based on those two inputs and the function output, they can always conclude regarding the possibilities of the other two inputs. That's fine. That's not a breach of privacy. Okay, so I hope this point is clear. Now, what we want to show here is that suppose adversary takes this snapshot and tries to analyze, and he wants to narrow down what exactly was the case. Was it this case, or was it this case, or was it this case, or other possible cases? We will be showing that for the adversary, it could be any possible case, which would have resulted in the values in bold, implying that whatever values in bold he has seen during the protocol from the honest participants, it does not reveal anything to the adversary. So for example, suppose adversary makes this guess. Can it be possible that x2 was 0 and x3 was 2? Because that's one of the possibilities, which along with x1 being 2 and x4 being 0 will lead to the value 4. Remember, adversary has seen this snapshot. Now, if x2 is 0, if indeed x2 would have been 0, and remember, the first share for x2 that adversary has seen was 2, and the fourth share for x1 which adversary has seen corresponding to x2 was 2. Now, if x2 was 0, then indeed that's possible, provided the B polynomial would have been this. Because if second party's input would have been 0, and if he would have selected this B polynomial, then that B polynomial when evaluated at alpha 1 would have resulted in 2, and when evaluated at alpha 4 would have resulted in 2. In the same way, if indeed P3 would have used the input 2, and if the first share for x3 was 3 and the fourth share for x3 was 4, then that is possible, provided P3 would have used this polynomial. And now you can see that if indeed P2 has used this polynomial and P3 has used this polynomial, that matches with everything that adversary has actually seen in the protocol. But adversary is absolutely not sure whether this is the case or not. Because there could be other possible cases as well. For example, he can make the hypothesis that is it possible that the second party's input was 2 and the third party's input was 0. Of course, the first and fourth inputs are freezed to 2 and 0 respectively. Well, this is also a possibility, provided the B polynomial selected by the second party was this constant polynomial, and the C polynomial selected by the third party is this polynomial. That will again result in adversary seeing 2 and 2 as the shares for x2 and 3 and 4 as the shares for x3, and then everything will match. In the same way, adversary cannot rule out this possibility as well. There is a possibility that P2's input was 1 and he has used this sharing polynomial, and P3's input was 1 and he has used this sharing polynomial, which would have resulted in the same bold values which adversary has actually seen. So now adversary can't rule out whether this was the case or whether this was the case or whether this was the case. That means he is as clueless as he was earlier. So earlier his view was that, okay, two of the inputs were 2 and 0, final output was 4. From that, he can immediately narrow down, okay, there are these many possibilities for x2 and x3. He would like to narrow down. But what I have shown here is that even though he can find various possibilities of x2 and x3, which could have resulted in the values in bold, among those possibilities, he cannot pinpoint what exactly is the case. And as a result of that, we can safely conclude that he has not learned anything regarding x2 and x3 additional. Okay. Right. So what basically we can say here is that the view of the adversary, that means this values in bold in the first table, it is consistent with every candidate x2 and x3. which along with x1 being 2 and x4 being 0 would have resulted in the sum 4. Adversary cannot rule out any particular x2 and x3. Okay. So is the BGW protocol for linear functions clear? We now have to consider the case when the circuit could have non-linear gates as well, which we have not considered yet. Okay. Right. Now, when I say non-linear gates, okay, before going into the BGW protocol with non-linear gates, let us again recall the linearity property of sum is secret sharing, which we had seen yesterday. We had seen that if you have linear functions, then you can compute any linear function of secret shared values by applying the linear function on the shares itself. That means, suppose if there was a value S, which was secret shared, and if there is a value C, which is publicly known, then to compute the secret shares of C plus S, every party just need to add the constant C to their respective shares of S. Or if you want to compute the shares of C times S, where C is known to all the parties, then every party just need to multiply C with their respective shares of S. That will give the parties their respective shares of C times S. Or if you have two values, S and S prime, which are secret shared, and you want the parties to compute their respective shares of S plus S prime, then again, that is very simple. Every party just need to add their respective shares of S with respective shares of S and S prime. Now, what about multiplication? Suppose there was a value S, which is secret shared. That means there was a t-degree polynomial A, whose constant term is S. And there is a t-degree polynomial B, whose constant term is S prime. And ith party has the value of A polynomial and B polynomial at alpha I. And this holds for all i's. My goal is to compute shares for S times S prime. What do you think parties should do? How can the parties compute their respective shares of S times S prime? Is it okay if the parties multiply their respective shares of S and S prime? What that will lead to? You post your responses here, because I do not have access to Zulip. So what will happen if the parties multiply their respective shares of S and S prime? Can I say that that will give the parties their respective shares of S times S prime? Okay. So let us do that. Let every party multiply their respective shares of S and S prime. That will give them a vector of values. What will be the property of this vector of values? The point is, this vector of values will constitute a secret sharing of S times S prime, but now the degree of sharing is 2t, no longer t. Because these values are nothing but the values of this polynomial, the A polynomial multiplied by B polynomial, which is now a 2t degree polynomial. Because A polynomial was degree t, B polynomial was degree t. And since you are multiplying the individual points on the A and B polynomial, the resultant vector of values will lie on a 2t degree polynomial. Of course, the constant term of this 2t degree polynomial will be s times s prime. That's not an issue. The issue is now that its degree is 2t. It's no longer t. Right? And more importantly, it will be not a random vector of shares. What does that mean? If this vector, so if I take all the other operations, the linear operations, suppose if this vector of shares was random, then even if every party adds C to that vector, the resultant vector will be random. Similarly, if I take this second operation, and if this vector of shares was random, and if every party multiplies their respective components with C, then that will still result in a random vector of shares. Same holds for this third operation. Two random vector of shares when added will lead to a random vector of shares. But now can I say the same thing regarding this fourth operation? You have two random vector of shares. You multiply them component wise. Will that lead to a random vector of shares lying on a 2t degree polynomial? The answer is no, because this vector of values now lie on a special polynomial whose factors are A and B polynomial. So I can't say that A times B polynomial, the A polynomial multiplied by B polynomial is a random 2t degree polynomial. No, it's no longer a random 2t degree polynomial. In fact, it's a polynomial whose factors are A polynomial and B polynomial. So now you can see that there are two issues here. We can't simply let parties multiply their respective shares of S and S prime and say that our BGW protocol, which we had discussed till now, will work even for the non-linear gates. No, it's not going to work because of two reasons. First, the degree of the shares has increased. So you can imagine the following. Suppose if you have a circuit like this, you have A times B, and then that is followed by C. Your function is A times B times C. Suppose A is secret shared, B is secret shared. You ask every party to multiply their respective shares of A and B. They come to this gate now. At this point, the degree of sharing is 2t. And now with those shares, if they multiply their respective shares of C, that will lead to a vector of shares for Y, where the degree of sharing will be 3t. If that is followed by a subsequent multiplication, and if you keep on asking the parties to multiply their respective shares, then that will simply keep on blowing up the degree of the sharing. And it might eventually blow up so much that you do not have sufficient number of shares towards the end to actually reconstruct the function output. And that's why now we are faced with a serious problem here. If there are nonlinear gates here, nonlinear gates means the multiplication gates, then we have to solve a problem which we call as the degree reduction problem. What's the degree reduction problem? An instance of the degree reduction problem will be the following. Suppose you have a multiplication gate in the circuit where both A and B are private. They are secret shared. Okay, that means the parties have NT secret sharing of A. When I say parties, I mean to say ith party have the ith component of this vector of shares. And in the same way, the parties have B, the value B being NT secret shared. I want a mechanism which allows the parties to get the value C NT secret shared. And in the process, nothing about the value A and nothing about the value B should be revealed. And this is called the degree reduction problem. Why it is called degree reduction problem? Because we want to reduce the degree. Because if just every party multiply their respective shares of A and B, then that will basically give them a vector of shares whose degree is now 2t. We want to reduce that degree from 2t to t. But in the process, no one should learn anything about the shares of A, the shares of B, and the shares of C. Everything should happen privately. Because if privacy is not an issue, then the problem is very simple to solve. Let the parties publicly reconstruct A, publicly reconstruct B, and then they can just compute, run the summary sharing algorithm on C. But that's not allowed here because this multiplication gate could be an intermediate gate in the circuit. And remember, in the BGW protocol, only the final output value is allowed to be publicly reconstructed. No intermediate value, no input value should be reconstructed. So this is an instance of degree reduction process. Okay. And intuitively, you might now have imagined that it requires some interaction among the parties. This is no longer like, so this is no longer like evaluating a multiplication gate, evaluating a linear gate, sorry. Because linear gates could have been evaluated non-interactively. The parties just need to apply the linear function on their respective shares of the gate input. Right? That means if it would have been a gate where you want to add A and B, then that's not an issue. Every party could have just added its share of A with its share of B. That's fine. But if it's a multiplication operation, they can't do this. Okay? Is the degree reduction problem clear? We have not discussed the solution yet, but is the problem clear? Right? Okay. So now let us proceed to the degree reduction solution. There are some various methods. There are various methods. So the original BGW protocol itself has a degree reduction method, but that's slightly involved. There is a very simple method, which is also called as GRR method, Gennaro Rabin. Okay. I'm going to discuss the GRR method. Okay. And now this degree reduction solution will require this condition to hold. Okay. So this was not necessary if the circuit has only linear gates, right? Because for the case of linear, where your circuit only has linear gates, we know that we can design a protocol even if t is less than n. But if your circuit has even one nonlinear gate, we necessarily require this condition because we have to solve an instance of degree reduction. It turns out that this is necessary condition for any generic perfectly secure MPC. It's not just because that BGW degree reduction method requires t less than n by 2, or just because GRR method requires t less than n by 2. This is a necessary condition. We can prove that there are lower bound techniques, but we will not see those lower bound techniques. I will just briefly explain the GRR degree reduction method. Okay. So what exactly we want to do here? So right now we have a value A, which is secret shared, say through an A polynomial. No one knows that A polynomial. It's a t degree polynomial. So that's why it's a random polynomial from this set. What exactly is this set? This is the set of all t-degree polynomials with small a as the constant term. No one knows this polynomial, remember, because this is the polynomial corresponding to a value a, where a is some intermediate value in the circuit. Same holds for the value b. The value small b is shared through some b polynomial whose degree is t, and every party has the ith point on that b polynomial. Okay, so this a1 is a polynomial at alpha 1, a2 is a polynomial at alpha 2, an is a polynomial at alpha n. And similarly, this b1, b2, bi, bn are the values of this b polynomial at alpha 1, alpha 2, alpha I, alpha n respectively. Okay, now here is how the GRR degree reduction method works. The first step will be, let every party multiply their respective shares of A and B. Let them do that first. So that means P1 multiplies A1 and B1, that will give him K1. P2 multiplies A2 and B2, that will give him K2. PI multiplies AI, BI, that will give her KI. Pn multiplies An and Bn, that will give him Kn. Now, what can I say about the points K1, K2, Ki, Kn? They lie now on a 2t degree polynomial, whose constant term will be AB. Let me denote that polynomial by K polynomial. So this K polynomial is A polynomial multiplied by B polynomial. That's why its degree is 2t. Okay. And what will be the constant term of the K polynomial? It will be the constant term of the A polynomial times the constant term of the B polynomial, which is A times B. Fine. But this is not the output which we want. We want a t degree polynomial somehow whose constant term is A times B, and every party should have the ith point on that polynomial. Okay. So now the crux of the GRR degree reduction method is the following. If I consider the value A times B, A times B is a linear function of these values K1, K2, Ki, Kn. Okay. Specifically, we can rewrite this K polynomial as a linear combination of several two-t degree polynomials linearly combined with these points K1, K2, Ki, K. Okay, how we get this? Okay, so the idea here is the following. The degree of K polynomial is 2t. And we are working with the assumption t is less than n by 2. That means n is greater than equal to 2t plus 1. That means if K1, K2, Ki, Kn are made public, then we can apply Lagrange's interpolation on alpha 1 K1, alpha 2 K2, alpha I Ki, alpha n Kn, and interpolate the K polynomial and compute k of 0, which is AB. You agree with this point, whatever I have written? Whatever I have written, do you agree with this? Assuming we are working with this condition t less than n over 2, which implies n is greater than or equal to 2t plus 1. It's a simple fact because these points k1, k2, ki, kn now lies on a 2t degree polynomial. And to reconstruct a 2t degree polynomial, we need at least 2t plus 1 points. And we are working in a system where we have at least 2t plus 1 participants. That means if somehow, if this point, if this values k1, k2, ki, kn are made public, then it's very easy to compute AB. This whole computation, basically this Lagrange interpolation, is nothing but a linear function of k1 to kn. What exactly is the form of that linear function? This is the form of that linear function. What are this delta 1 polynomials, delta 2 polynomials, and so on? Well, there are some. Okay, so if you want delta 1 polynomial, it will have the form x minus alpha 2, x minus alpha 3, and like that, x minus alpha n times alpha 1 minus alpha 2, alpha 1 minus alpha 3, and so on. People who have studied Lagrange interpolation might be knowing this, but if you don't know that, then also it's fine. Similarly, the form of delta 2 polynomial will be x minus alpha 1. In the numerator, you will have all the roots except alpha 2. And then in the denominator, you will have alpha 2 minus alpha 1, alpha 2 minus alpha 3. Okay, so they are your delta polynomials. So basically, the idea here is that as part of this Lagrange interpolation, this relationship holds. And this further implies that the value k0 can be expressed as a linear function of k1, k2, kn, where the linear combiners are delta 1, 0, delta 2, 0, delta n, 0. So here, let me erase all these things. What we can say here is the following. From Lagrange interpolation, this value k0 can be expressed as a linear function of k1, k2, kn, where delta 1, 0, delta 2, 0, and like that, delta n, 0 are linear combiners. And they are publicly known. They are independent of k1, k2, kn. That's a important fact, important point from the Lagrange interpolation. Okay. So any question regarding this point, that k0 can be expressed as a linear, and k0 is nothing but AB, because the constant term of the k polynomial is AB. So the summary here is that the value A times B can be expressed as a linear combination of k1, k2, ki, kn, provided this condition t less than n over 2 holds. Okay. Any doubts regarding this? Okay. So there are no doubts. So now let's proceed. First, fine, we can express AB as a linear function of K1, K2, Ki, Kn. But then the points K1, K2, Ki, Kn, they are not publicly available. They are available only with the individual participants. So K1 is available only with the first participant. K2 is available only with the second participant. Ki is available only with the ith participant. And the Kn is available with the nth participant. And we cannot make K1, K2, Ki, Kn public. Because if we make K1, K2, Ki, Kn public, then that will end up making A, B values public, which we don't want to do. These values C1, C2, Ci, Cn, they are public. K1, K2, Ki, Kn are private. That's why they are in red color. They are available with only with the individual parties. So now the idea behind the GRR degree reduction method is that, okay, now we have a linear function here which we want to securely compute. Okay, and what are the respective inputs of the parties for this linear function? They are K1, K2, Ki, Kn. And we know how to securely compute any linear function using the BGW method. That's what we have discussed at the beginning of today's lecture, right? So we know how to securely compute a linear function, and then we can apply now that method here to get a secret sharing of AB, where the degree of sharing will be T. Okay. So what P1 will do now? P1 will act as a dealer, and he will compute this vector of shares by running an instance of secret sharing, Samir secret sharing, and distribute the shares to the respective parties. In the same way, the ith party, he will take the value Ki and share it through a random T degree polynomial. And the nth party, so basically the idea behind the GRR degree reduction method is to exploit the fact that A times B is a linear function of this product share. So let me call these values K1, K2, Ki, Kn as product shares. Why I'm calling them as product shares? Because they are products of the individual shares of A and B. And we cannot afford to make these product shares public because they are available with the respective parties. But what we know is a method to securely compute linear functions. So think of the GRR degree reduction method as an instance of BGW protocol for securely computing this linear function. So P1 will go, it will act as a dealer, it will take its product share K1 and secret share like this. Pi, it will take its product share Ki and it will run an instance of Samir secret sharing and share its product share. And Pn will take its product share Kn, run an instance of Samir secret sharing and secret share it. All of them are now secret shared through degree T polynomials. And now your goal was to compute this function in a secret shared fashion, where the combiners are publicly known. The combiners are C1, C2, Cn, namely the values delta 1, 0, delta I, 0, delta n, 0. They are publicly known. So parties can apply this linear function on their respective components of this product shares of the shares of the product shares. And that will lead to a vector of shares lying on a polynomial of degree T. Because now this linear operation is performed on vector of shares, all of which lie on T degree polynomials. And a linear function applied on vector of shares lying on T degree polynomial will give you another vector of shares lying on T degree polynomial. So that's a degree reduction method by GRR. You can imagine, again, so pictorially, the whole idea is that this is your input for an instance of degree reduction, and this is the required output. This is obtained basically by securely computing this linear function, where the inputs of the respective parties are the product shares K1, K2, Ki, K. Okay. How much round it will require? It will require only one round, because each party can independently and parallelly secret share their respective product shares. How much communication it will require? It will require n instances of summit secret sharing. So, and one instance of summit secret sharing requires a communication of n field elements. So that's why total n square field elements. Okay. Any doubts regarding the GRR degree reduction method? Okay, so there are no doubts. Then let's see a concrete example, a circuit where we have both linear gates and non-linear gates. Okay, so in this circuit, we have a linear gate, we have a non-linear gate, and then again a linear gate. And the goal of the parties is to compute this output Y. And we will be working with a setting where T is less than n over 2. We are taking the case where n is equal to 4. So what will be the first step? The parties will respectively secret share their inputs. So suppose the input x1 is secret shared and resulting in this vector of values. Input x2 will be secret shared, resulting in this vector of shares. X3 will be secret shared, x4 will be secret shared. So inputs are done. Now we come to the first linear gate here, whose inputs are x1 and x2 and output is I1. That if this is a linear gate, the parties can simply apply the linear function on their respective shares of x1 and their respective shares of x2. So that means they have to component wise add. That's all. That will give them their vector of shares for this intermediate value I1. No one knows the value of I1 at this moment. Everyone is happening over the shares. So this gate is done. Now what's the next gate in the circuit? As per the topological ordering, this multiplication gate. What are the inputs? X3 and X4. Are they secret shared? Yes, they are secret shared through degree T polynomial. So what parties will do? The parties will run an instance of GRR degree reduction, where the inputs for the instance of GRR degree reduction will be these two vectors of shares. So what parties will do? They will locally multiply, compute product shares, and then every party will share its product share, apply the Lagrange linear function, and then they will come to this vector of shares. This vector of share will now constitute points on a T degree polynomial whose constant term will be I2. That means this multiplication gate is done. No one learns the value of X3, no one learns the value of X4, no one learns the value of I2. Now what's the next gate in the circuit? Plus gate, as per the topological. Okay, as per the topological ordering, next gate is plus gate. What are the inputs of this plus gate? I1 and I2. So the parties will focus on these two vector of shares, and this is now a linear gate. They can simply apply the linear function and come to the vector of shares corresponding to Y. This gate is done. Now no more gates are left in the circuit. Broadcast. So each party makes its share of Y public. So P1 makes Y1 public, P2 makes Y2 public, P3 makes Y3 public, P4 makes Y4 public. And that's why the whole vector is now publicly available. It's a T degree, it's lie on a T degree polynomial, and then they can reconstruct back the function output Y. And then throughout this process, what has happened is all the inputs were secret shared through T degree polynomial. All the intermediate values were secret shared through a T degree polynomial. Only the final output is reconstructed. That's why the privacy of the inputs of the parties is maintained. Any question? Okay, so if there are no questions, let me proceed. So this is regarding the complexity analysis. I can skip it. I will just quickly go through a special case of MPC for a small number of parties. Specifically, we will see the case of secure three-party computation. The scenario or the setting here is the following. We have three parties, P1, P2, P3, inputs X1, X2, X3 respectively. And P is equal to 1 here. That means any one of these three parties can be corrupt. We want to perform secure computation. That means we want to compute this function securely. Of course, one can say that since now we have a BGW method, we can run the BGW method for the case where n is 3 and t is equal to 1. So we already have a protocol. Why we want a special 3PC protocol? The reason we will go for special 3PC protocol is it will be more efficient compared to the protocol which you will obtain by substituting n equal to 3 and t equal to 1 in the generic BGW protocol. That means we will be exploiting the fact that we are working only with n equal to 3 and t equal to 1 and design some cute techniques which are tailor-made only for n equal to 3 and t equal to 1. They can't be generalized for higher values of n and higher values of t. Okay, and there are several motivations for studying this specific setting of secure 3PC. As I said, we will be having, we can have customized solutions tailor-made only for this specific setting, which will be more practically more efficient than the generic solutions. And more importantly, in these protocols, you can perform computations even over a ring. You don't even need a finite field to perform operations. Okay, so even if you are working or if you are performing operations over a ring, that's fine. So these are some of the motivations. Okay.
Sir, sorry to interrupt. There is a comment from Dibakar in the chat window. He was not able to follow the reconstruction process for nonlinear part.
So reconstruction happens only for the function output, not for the, is that not clear? That's the standard Lagrange interpolation. Which part of the reconstruction is not clear? See, okay, let me go back. Getting back the original values. Which original values? Is the doubt in this specific slide? Where? Example. Here. So this example, right? Which x values? Getting back the x values. Where we are getting the x values?
I can unmute
yeah, please.
Dibakar.
Yeah.
I will do that. Okay. Yeah. Dibakar, you can unmute yourself and talk.
Yeah. Am I clear? Audible?
Yes.
Okay. No, sir. Actually, in the linear case, we were actually getting back after computing the function. We were able to retrieve the the values. In this case, how are we going to get that? I mean
this step. Okay. In this particular step, when all the gates have been computed, now parties have reached to the output value. So that means at this point, Y is secret shared. So see, you have not seen the animation. When I remove this box, I mean to say everyone broadcast their shares of Y. So Y1 is sent to everyone, Y2 is sent to everyone, Y3 is sent to everyone, Y4 is sent to everyone. And then they apply the interpolation and get this polynomial. If they get this polynomial, its constant term is the function output Y.
Okay, yeah, correct. Yes, thank you.
Yeah, it's written here, right? Output publicly reconstruct the secret shared output.
Yeah, That part of the screen is not visible actually. I don't know why. Okay.
Okay. Okay. No problem.
Okay, fine. Yeah. Okay. Yeah, fine.
Yeah.
Thank you.
Okay. Thank you. Right. So we will now go to three-party computation. Right. We will see a tailor-made protocol only for the three-party case. Now the
question from Vanishree. Can a secret sharing scheme be nonlinear?
Here we considered non-linear gates degree. Very good question. I will answer that at the end of the lecture. Very good question. Okay. So since we want to design tailor-made protocol only for the case of three parties, we will use a different form of secret sharing. We will not use Samir secret sharing. Of course, you can run the protocol with Samir secret sharing, but that will be not as efficient, which we want right now. So this is a special form of secret sharing called replicated secret sharing, RSS, which is only for three-party case. Now we will be performing all the operations over a ring, which is not a field. And we will say a value is secret shared in replicated form. A value S is shared in the replicated form if the following holds. S should be splitted into three shares, S1, S2, S3, such that S is the sum of S1, S2, S3. And every party will have two components among these three components. So P1 will have the first and second component, P2 should have the second and third component, and P3 should have the third and the first component. If this is ensured, then we will say that the value is replicated shared. Okay, so this is a different form of secret sharing. Now you can see that if a value is secret shared in this form, then even if one of the parties is corrupt, it won't be learning the full value S. So for instance, if P1 is corrupt, it won't be knowing what is S3. And if it does not know S3, it cannot find out what is S. So you can see any single party, he will be missing at least one of the three shares, and that's why he won't be knowing anything about the secret. But if two parties come together, say P1 and P2, then they will have all the three pieces, and hence they can reconstruct S. So this is indeed a 3-1 secret sharing. Okay. And it is easy to see that this 3-1 replicated secret sharing satisfies your usual linearity properties. That means if there is a value S, which is secret shared in this form, and if there is a value S prime, which is secret shared in this form, and suppose C and D are public constants, and your goal is to compute shares of C times S plus D times S prime. Then without even performing any interaction, each party can compute its respective shares for C times S plus D times S prime by performing this operation. Okay, so like your Samir secret sharing, this secret sharing also has your linearity property. How can a party secret share its input in this format? So imagine P1 wants to secret share its input S. P1 has an input S, which it wants to secret share. So what it can do is it can compute three random shares S1, S2, S3, which sum up to the value S. And then to the second party, it can give S2, S3, and to the third party, it can give S3, S1. Okay. And if any one party is corrupt, say P1 is not, of course, P1 is the dealer here. If P2 or P3 is corrupt, it will fail to find out what is the input of the dealer P1. In the same way, if P, yeah.
Sir, I have a question. is it this protocol, since it doesn't have Lagrange interpolation, this protocol can work over rings or?
Yes, yes. So
okay.
so we can operate over Boolean rings as well.
Okay. So if there is the inverse required from the Lagrange interpolation point of view, any protocol can work over rings. Is it, or only this specific protocol?
Yeah, so this specific protocol works over a ring, and there is another three-party protocol which is there in my presentation, but I won't be able to discuss, which also can work over a ring. Basically, wherever you don't need inverse, you can work over a ring. Yeah.
Oh, yes, sir. Yes.
Okay. So what will be the communication complexity of this sharing mechanism? The dealer has to communicate 4 ring elements. Now we can make it more efficient. How we can make it more efficient? We can do some pre-processing. Pre-processing in the sense that suppose when the parties are free in the sense there is no computation happening, no MPC protocol is running, and they are sitting idle. So they can generate some data which is independent of the actual circuit, independent of the actual inputs, which they can generate in a phase which we call as a pre-processing phase, which will be independent of actual circuit evaluation. And later, when the actual circuit evaluation happens, using the data which has been generated in the pre-processing phase, they can perform the computation in a faster way. That's the whole motivation here. So what's the pre-processing phase can do here is the following. Suppose there is a mechanism in the pre-processing phase which allows the parties to generate a secret sharing of the value 0. Namely, somehow the parties can come up with shares alpha 1, alpha 2, alpha 3, not in the replicated form. Every party will now have only one piece here, such that those 3 pieces sum up to 0. Suppose this has been already done in the pre-processing phase. How? We can see later. Now, actual sharing happens in the following way. Suppose P1 has an input S, which it wants to secret share. We now do not want to follow this process. We want a more efficient process because that process has a communication of 4 ring elements. We want to reduce it. The input for the P1 is the dealer, suppose. Its input is S. It wants to secret share S in the replicated form. What we can say about S plus alpha 1 plus alpha 2 plus alpha 3? This will be S only. And parties already have their respective components alpha 1, alpha 2, alpha 3. Now to make sure that the value S is available in the replicated form, what P1 has to do or what dealer has to do is the following. It just has to compute this value and give it to the third party. The third party has to give alpha 3 to the second party, which also it can do, which it could have done in the pre-processing phase itself. And the second party should send alpha 2 to the first party. Okay, and now this brings down your communication from 4 ring elements to 3 ring elements. So you might be wondering what's the saving from 4 to 3? Only 1. But in actual circuit evaluations, in practical circuit evaluation, we have millions of values which needs to be secret shared. So that means a saving of 1 ring element for 1 instance of secret sharing implies a saving of millions of ring elements being communicated. That means if you would have done some pre-processing already, then actually when you have to perform the secret sharing at the runtime, you can perform better by several order of magnitude. Okay. How exactly this pre-processing data can be generated? It's there in my presentation. I will skip through it, okay, because I'm running out of time. Now, this replicated secret sharing also has a reconstruction algorithm, which is very simple. If two parties are there who wants to reconstruct a value, remember this is an instance of 3-1 secret sharing. So if two parties come together, how they can reconstruct, or suppose if all the three parties come together, how they can reconstruct. Each party just has to send one ring element to another, because each party is missing only one piece of information. Okay, that one piece of information can come from its neighbor. That's all. So this requires a communication of 1 round and 3 ring elements. Now, since this replicated secret sharing satisfies the linearity property, I can evaluate the linear gates in my circuit non-interactively, but evaluating multiplication gates will be a challenge, because like the BGW protocol, where just by locally multiplying the shares, the degree of the sharing in blow-ups, we also face a similar issue here. So imagine you have two values, X and Y, which are secret shared as per this semantic. Okay, and our goal is to securely compute a replicated secret sharing of X times Y. Now, if I expand X times Y, then it will be basically summation of all ij xi yj. Okay. So you might be tempted to do the following. Let P1 compute this partial product. It can do so because it has X1, it has Y1, it has Y2, it has X2. In the same way, let P2 compute this partial product and P3 compute this partial product, and let them exchange their respective partial products to each other. And now you can say that P1 will have Z1, Z3, P3 will have Z3, Z2, and P2 will have Z2, Z1, and altogether Z1 plus Z2 plus Z3 is equal to Z, which is XY, and hence we have achieved our goal. If you see here carefully, we have not achieved our goal because there is a secure privacy breach. What's a privacy breach? If we follow this procedure and allow the parties to exchange the partial products as it is with their respective neighbors, then suppose, for instance, if we consider the case where P2 is corrupt. Now, when P2 is corrupt, he already has these information, and now he is receiving Z3. Z3 is this value. In Z3, X3 times Y3 is already known to the adversary. I'm considering the case when P2 is adversary because he has already X3, he already has Y3, fine. But earlier, he did not have anything regarding X3 times Y1. And earlier, he did not have anything regarding X1 times Y3. But when I am giving him Z3 in clear, he ends up learning this partial information. And this might end up revealing X3 and Y3. And if X3 and Y3 are revealed to P2, he ends up learning X and Y. So definitely this is not the right approach. Okay, this is not the right approach to do the multiplication. But the idea will remain the same. What parties are going to do is they will exchange the partial products, but after randomizing them. Okay, so how they can randomize? Again, we will assume that there is some pre-processing data available with the parties. The pre-processing data is again the same, namely a secret sharing of value 0, which they would have generated in the pre-processing phase. And now the observation here is that the summation of Z1, Z2, Z3, along with alpha 1, alpha 2, alpha 3, will give them the value z only, which is xy, because alpha 1, alpha 2, alpha 3 sums up to 0. So that's the idea parties are going to do. So now P1 will send the partial product to its neighbor, but it will randomize it by adding alpha 1. P3 will send Z3, namely the sum of the partial products, but after randomizing it with alpha 3. And same P2 will do. It will randomize and then send. Now the attack which I had shown earlier, it won't work. So this is a very practically efficient 3PC protocol compared to the generic BGW protocol. You might be wondering, why can't we run it for n equal to 5 and t equal to 2? Why can't we run it for n equal to 7, t equal to 3, and so on? You can see that if we keep on generalizing replicated secret sharing for these higher cases, then the number of shares which each party has to keep will increase exponentially. So right now, each party has to keep 2 pieces out of the 3 pieces. If we keep on increasing the threshold, then the number of pieces which the parties have to keep increases exponentially large. And that's why it is efficient only for the case when n is equal to 3 and t is equal to 1. So with that, I stop. There are plenty of other things which I can talk about, but due to interest of time, I am not going through the details. As I said, you have references available here, these 2 NPTEL courses. If you want, you can go through them. And some advertisement. I am always looking for motivated MS and PhD scholars. If you are interested, you can respond. You can apply in response to the advertisement. But I do not offer internship or project position. I do not read those emails as well. So because short-term research does not happen, you have to come here for either an MS or a PhD. Okay. So I will be now happy to take your questions regarding the nonlinear secret sharing scheme. Yes, we have nonlinear secret sharing schemes, but using that, you can evaluate only the nonlinear gates in a non-interactive fashion. You will have to do some kind of degree reduction for the linear gates. So basically your question was, can we have a secret sharing scheme which allows all the gates to be evaluated in a non-interactive fashion? Unfortunately, no. Either you can evaluate only linear gates freely in the sense in a non-interactive way, or only non-linear gates in a non-interactive way. You can't have a secret sharing which allows you to evaluate both kinds of gates in a non-interactive fashion. Any other questions?
Sir, any use cases for MPC working on embedded devices?
Embedded devices?
Yeah, so far I've seen MPC, most of the times I've seen only ML use cases.
I have no idea. Sorry.
Okay, other than ML, what can be the possible use cases for ML? Sorry, MPC applications.
Any computation where you have privacy issues, where you have distrusting entities who do not want to leak their data to each other.
Okay.
Good. ML is just one case. You can have plenty of such use cases.
Any limitation on the computation of the device, like while designing the protocol?
Yeah, that's a good question. So that's why we go for information theoretic, the secret sharing based protocols. They require relatively less computation compared to your garbage circuit based MPC, where the magnitude of computation is enormously large.
Okay. Yes, sir. Yeah. If there is a question from. Yes, sir. Yeah, please continue. Sorry.
What is this real world, Siddharth Lal? What could be a real world example mean? Yesterday I gave you so many motivational problems. Secure auctions. You want to compute. You want to perform compute statistics over the database of companies. without disclosing the database. So many use cases are there. Were you there in yesterday's session, Siddharth Lal? The first 10 minutes I spent on the motivation only. You learned about HE, but I talked about the applications for the first 10 minutes. Yes, HE is also one way of performing secure computation, but they are not practical enough as of today to deploy it on a large scale. Okay, so there are no more questions?
Yes,
Yeah.
yes. I've even checked the Julip chat also. There are no questions on Julip. Thank you so much, Professor Ashish, for the wonderful talk and motivating the students to further explore MPC. I hope they can go to the NPTEL site and understand the course in detail.
Okay.
Thank you so much for your time, sir.
Okay, thank you.